So welcome everyone to the first press conference of the 245th meeting of the American Astronomical Society. We are here in National Harbor, Maryland, and we are gearing up for a very big week. It is Monday, January 13th at 10:15 a.m. Eastern Time, and we're here for a feast of feasting black holes. So my name is Susanna Kohler. I'm the press officer for the AAS, and I'm assisted here today by Carrie Hensley, the deputy press officer. And we'll also have AAS media fellow Lexi Galt here this week, helping out with the press conferences. And Rick just walked in the room, and I'm going to be leveraging him. Hi, Rick Feinberg, former press officer. He's going to be running the mic during the Q&A session. Congratulations, Rick.
Without having any responsibilities, I wasn't sure what to do around here.
And now you've got responsibilities. Congratulations. So I just wanted to take a moment before we get started to acknowledge the ongoing situation in California with the wildfires and recognize that a lot of us here have friends and colleagues and family in the area who have been affected, and many folks who wanted to be here at the meeting who aren't able to make it now. So you'll note there's a rotating slide deck that plays before every session in the room, and one of the slides in there is a list of current resources, relief efforts that are accepting donations for the wildfires if you're looking to do something. Just wanted to mention that. But for those of you who are here, I'm so glad that you're here. Thank you for being here, and we have a really exciting week ahead for you. We're excited about the press program and our lineup, and we have a packed week ahead of you because this is a big meeting. We've got, at last count, I saw over 3,500 attendees, which is very close, I think, to a record for a AAS meeting. It is a record. 3,654. Thank you. Rick Feinberg comes in with the numbers. Who could have doubted it? All right, so we're at a record attendance for a AAS meeting, which is great. So we have a very busy press program all week. I guess I can take this off. So we're going to be here all 4 days of the week, one in the morning at 10:15 and afternoon at 2:15 with press conferences. We've got 8 of them. And then on Thursday, we're also hosting a seminar for science writers at 12:45. That's going to be a backgrounder with information for the media on the Vera Rubin Observatory, which is preparing for first light this summer. And then one last note about the press program. We are hosting a press meet and greet event, informal small event, but we really encourage those of you who are press registrants on site to come by today, 12:45 at the press office next door. And this is just an opportunity to kind of see who's in town, say hello to your colleagues and friends, meet new people. And we're really hoping that some of the early career science communicators on site here will have the chance to sort of interact with the more seasoned veterans present. So with all of that said, let's go ahead and get down to it. If you could please silence any cell phones or things that make noise, that would be appreciated. Note that we are recording this press conference. We're streaming it to YouTube, and you can find the video for this after the press conference and all of the other materials for the press kit. It's in the press kit. You can get to it through the press section of the meeting website, and it's also linked from the Slack channel, press conferences. Hashtag press-conferences, I think. And we'll be keeping that up to date throughout the week. So the way we're going to do this, if you've never attended a press conference before, is we're going to go through, I'm going to give a brief introduction to the topic and to each of our speakers and their subjects. And then the speakers will go through in order and do all of their presentations. And we ask that in that time you hold all of your questions, and we'll get to a joint Q&A session at the end. So then a whole panel session where everybody can answer your questions. We'll have a mic in the room running around. Thank you, Rick. And for those of you who are online, you can go ahead and queue up your questions. If you're watching via Zoom, you can queue them up via the Q&A box. We ask that if you put a question in there, please identify yourself, your affiliation, and who your question is for. And we're going to ask the same thing of the folks in the room. With that, I think we can talk about this session. So this is a feast of feasting black holes. All of the talks in this session are going to be talks about, in particular, supermassive black holes in the centers of active galaxies and what they are up to. So first up, we're going to have Eileen Meyer from the University of Maryland, Baltimore County, who's presenting on witnessing the birth of a new plasma jet from a supermassive black hole. Then Megan Masterson from the Massachusetts Institute of Technology will present rapidly evolving X-ray oscillations in the active galaxy, and I'm not going to give its serial number here, but in an active galaxy. Then Peter Boorman from Caltech is going to discuss uncover of supermassive black holes in our cosmic backyards with NuLANDS. And last up, Olivia Achenbach from the United States Naval Academy will present on the discovery of a newborn quasar jet triggered by a cosmic dance. So if you are ready, Eileen, I will go ahead and get your presentation up.
Right. Thank you, Susanna. So I'm Eileen Meyer. I'm an associate professor of physics at UMBC, and I'm really excited to tell you about this remarkable discovery that we made in a nearby supermassive black hole that actually became active and launched jets of gas, hot gas, while we were looking at it. And so why are we excited about this? Well, this particular black hole resides in a nearby active galaxy. So an active galaxy just means one where the supermassive black hole at the center is actively accreting material. So the figure shown at far left is a nearby galaxy with an AGN at the center. The one just next to it is a normal galaxy. So you have galaxies that look quite a bit like each other, but something will trigger that process. And the active galaxy, the active accretion process can last for millions of tens or hundreds of millions of years. And it's probably happening in 5 to 10% of galaxies at any given time. So we expect that the timescales for these things to turn on and to turn off are long, and certainly longer than, say, a human lifetime, or at least that was kind of our naive expectation earlier on. I will also mention the figure shown at far right is an active galaxy. You can see the host galaxy there with these very prominent jets of plasma coming out that we sometimes call radio jets because it produces a lot of radio emission. And that's how they're usually discovered. And that's only a small fraction of accreting black holes. And we would really like to understand how AGN turn on and off, how jets turn on and off. It's something that we have not really understood yet. And so that brings us to the star of this show. That is the Galaxy 1ES 1927 plus 654, which is getting not one, but two talks at this session. It is circled in red there to distinguish it from the foreground stars that are nearby. So this galaxy is called Changing Look because it did something remarkable back in 2018. It suddenly became 100 times brighter over the course of a few months. That is very, very unusual. We have discovered only a handful of these systems and none has been as well observed as this one. So when that happens, that means it's a completely different animal. We would classify this as a totally different kind of source, and naively, we would not expect a sort of a low-level quiescent black hole to become this. Back when this happened, there was some speculation that this looked similar to something called a tidal disruption event, which is where a gas cloud or star gets too close to a not active black hole, gets shredded and kind of briefly flares up and produces a lot of fireworks. So the black hole was already active. And so this makes this source interesting. We kept following it. I got involved back in 2021 when I was contacted by Sebastian Lacha, my colleague at NASA, to look Megan is going to talk more about that in the next talk. But you can see that for a long period, the radio, which is the lower panel, was doing not much. And that's what we expect from these active galaxies that don't have jets. They just have very low level radio emission. In response to the X-rays starting to pick up again in late 2022, we decided to start looking at it a bit more on the radio. And it was very fortunate timing because we caught it basically going exponential and increasing its radio output by a factor of more than 60 at its peak. And we've been following this, and it's continued to be at this much higher level now for over a year. And so this is unprecedented. We've never had this happen. We've never been looking at a black hole and watched it go from being radio quiet to suddenly very radio loud. And so normally this level of radio emission would tell us that there are jets, that this black hole is now producing oppositely directed jets of very hot, very energetic plasma. And in fact, we see that that is corroborated by the very high resolution radio imaging that we have. So this is a a movie or maybe more like a time-lapse video showing you very, very high resolution deep into what's happening close to the black hole. So the scale bar there is less than a light year, right? So that's kind of typical distance between stars and a galaxy. So we're getting very small scales. The black X is where the black hole is, and we can see that initially there's nothing, and then there's this emergence of these blobs, which is the hot gas being emitted on either side of the black hole, and we've actually followed it long enough to see that it's expanding away from each other. So these blobs look to be moving at something like 33% the speed of light. So that's these are extreme and energetic events, and we care about this because something like that going off in your galaxy is certainly going to change how that galaxy lives out its life. So in summary, this nearby black hole has turned on a radio emitting jet moving the speed of light. Never observed that in real time before. We've had a handful of other cases where we've maybe seen some later higher radio emission, but nothing this detailed. We do think it's probably related to that earlier tidal disruption-like event that occurred in 2018. In fact, there's been some very recent work suggesting that there's a class of black holes that produce not these monstrous jets that live for millions of years and exceed the host galaxy, but rather a little bit more downsized. They're called compact symmetric objects, and they only live for maybe 1,000 years, and they're thought to be triggered by a single ingestion or single tidal disruption type event. And so it's very, very possible that's exactly what we just saw, what we just witnessed here. And so that's very exciting for us, and to talk to theorists about how we can better understand how these black holes power and produce these jets. So with that, my contact information is on the slide, and that QR code should take you to the AppJ paper. It was put out today, so that paper is available. And if you have any questions, please reach out to me.
For those of you in the door, there is more space in here. Please come on in. There's some seats up front.
All right. Hi, everyone. My name is Megan Masterson. I'm a PhD student at MIT working with Professor Erin Kara, and I'm really excited to be here today. Are we good? Okay.
That message that is. Oh, sorry. Spoiler alert. Punchline. Please continue.
Yeah, okay.
Apologies.
All right. Yeah. Hi, everyone. I'm Megan Masterson. I'm a PhD student at MIT working with Professor Erin Kara, and I'm really excited to be here today to continue the story of 1ES 1927 plus 654. This is the same source that Eileen just talked about. And in particular, I'm going to be focusing on the X-rays and our discovery of these rapidly evolving X-ray oscillations in this source. So Eileen just gave you a really nice overview of the kind of multi-wavelength picture of this source and how it's evolved since 2018. What I want to highlight is that this source has been extensively tracked in the X-ray band. And you can see that it varies in brightness a ton over the last 6 years. And we really have an exquisite X-ray campaign and an exquisite data set to be working with. So in particular, we have over 1,000 observations with NASA's NICER Space Telescope on the International Space Station, and over 15 observations with XMM Newton led by ESA. And today, I want to kind of focus on really short timescale variability, timescale of roughly 10 minutes or so. And to do that, we're going to zoom in on these one of the X-ray observations with XMM Newton here. So this is from early on in the outburst, and I'm showing you this to kind of give you perspective for what we usually see in terms of how AGN vary in the X-rays. So in particular, this is a relatively typical X-ray light curve that you would see from an accreting supermassive black hole. There's a lot of variability, and this variability is relatively random. However, if we look at some of the more recent observations, what we're now seeing is this periodic oscillation. Essentially, the X-rays are rising and falling on timescales of roughly 10 minutes. These sorts of oscillations are extraordinarily difficult to detect around supermassive black holes, and there's only a handful that have been discovered to date. So this discovery was exciting in and of itself. But really what's really excited me is that we've seen a dramatic change to the period of these oscillations over the course of the recent 2 years that we've seen them. So in 2022, we saw that these oscillations had 18 minutes. And since then, the period has dropped to about 7 minutes. And it seems to be kind of stabilizing around this 7-minute period point. And this will be important and will come up later in the talk. So I want to spend the next bit of time talking about what could possibly be producing these oscillations. So one possibility connects nicely to what Eileen was just talking about with the formation of this new jet. So in particular, we think that a lot of the X-rays in AGN are produced very close to the supermassive black hole. And so in particular, the X-rays might be coming from the base of the jet, and that base of the jet might itself be oscillating. That's what this movie is showing you here. And in order to get the period to shrink, you essentially need to shrink the size of the base of that jet. But there's another kind of natural explanation for what could be producing this sort of oscillation, this periodic nature here. And that's orbits. Orbits naturally give you this nice periodic behavior. And in particular, there's a really easy way to get your period to change when you're in an orbit, and that's to change the actual distance of that orbit. So this movie here is showing you just that if you move something closer to that central objects, the period will shrink, the orbit is faster. And you can also think of this in terms of a local solar system analog. A Mercury year is shorter than an Earth year because Mercury is closer to our sun. This also helps explain why 1ES 1927 is so interesting, why these oscillations are so exciting. And that's because recently we've started discovering a bunch of these relatively long period transients in the nuclei. These have typical periods on the order of hours to days, which again means that they are coming from much further from the supermassive black hole. But if we scale down to 1ES 1927's roughly 10-minute period that we're seeing, we need to be very close to the black hole and basically on the edge of that accretion disk. So this is really allowing us to kind of probe the extremes of these orbiter models that are becoming really exciting in the era of gravitational wave astronomy. In particular, the period that we've tracked, and specifically this stabilizing at a roughly 7-minute period, tells us something really interesting about the companion of this source. So if this is an orbiter, it cannot be a black hole. If we had another stellar mass black hole in this system, that black hole would be, well, any source moving closer to a supermassive black hole is going to be emitting gravitational waves. And as you get closer and closer to that black hole, you emit more and more gravitational waves. These gravitational waves carry away energy and shrink the orbit. If we had a stellar mass black hole in orbit around the supermassive black hole, that would plunge directly into the event horizon quite quickly. Instead, to get this kind of period stabilization that we're seeing at around 7 minutes, we need some additional source of energy in order to be able to keep this object outside of the black hole's event horizon. And so that's why we think that this is a white dwarf. A white dwarf is the remnant of a star like our own sun, and it's very compact, but it can shed some of its matter onto this supermassive black hole. And that process of mass transfer can actually give you a little bit of extra energy and angular momentum to keep you outside of the black hole's event horizon. So I think this is really exciting. These observations have kind of directly allowed us to constrain what the potential companion is. And in particular, if there is a white dwarf in orbit around 1ES 1927 supermassive black hole, this has really exciting implications for gravitational wave astronomy and doing multi-messenger astrophysics. So in particular, what I'm showing you here is just kind of phase space of what will be detectable with the next generation of gravitational wave detectors like LISA. So those long period transients that I discussed earlier are on the lower frequency end of things, and it's unclear whether or not they will be detectable with LISA. However, 1ES 1927 sits right in this sweet spot of detectability with LISA. And because that white dwarf is so close to the supermassive black hole, we predict that if it is indeed in orbit, we will be detecting it in the 2030s when LISA launches. So in summary, we've discovered these rapidly evolving X-ray oscillations from an extreme supermassive black hole that we propose could be the result of either jet oscillations or a white dwarf in orbit around the supermassive black hole. And if it is indeed a white dwarf, we predict that this will be detectable with next generation gravitational wave detectors. Thank you.
Hi, everyone. My name is Peter Boorman. I'm from Caltech, and I'm here today to tell you a bit more about some exciting first results from the NuLANDS survey, all about how supermassive black holes grow. So let's get into it. So we've heard a bit today about active galactic nuclei or growing supermassive black holes, but I just wanted to put it into a bit of perspective for this talk. The relative size scales of a supermassive black hole to its host galaxy is effectively the size scales of a pea to the Earth. But yet, despite those extreme size scale differences, an accreting supermassive black hole has the potential to unleash havoc or positive influence as well to the host galaxy itself. So it has a dramatic implication for our perception of galaxy evolution and what we understand for those processes. But there's one component of this picture that I think is often overlooked, which is the subject of this talk, and that's the obscura. Right. You cannot have a growing supermassive black hole without some kind of reservoir of material that it's feeding from. And it's believed that this material can form the approximate geometrical shape of a donut. And depending on the orientation of that material towards our line of sight, which you can see in this graphic, as the orientation changes, you either see down to the center of the accreting material, which is very bright, or you see heavy obscuration if you're seeing through the wall of that obscura. Now, if our eyes were able to detect X-rays, the sky would be full of dots, right? And every single one of those dots would be an accreting supermassive black hole. Now, this image is quite remarkable. This is a few years old now, but it's an image from the Chandra Space Telescope. This is effectively what you get when you mix a region of sky that's relatively small, about the width of the moon, with an X-ray telescope that has exquisite angular resolution. This holds the world record for the most AGN that's ever in one individual picture after 81 days of exposure. It's about 5,000. But for the purposes of this talk, I think it's kind of interesting to think about what we don't see in this image. So there are now firm predictions that around 30 to 50% of all AGN should be so heavily obscured that they're effectively hidden. And so what this means is that in this picture that has a remarkably high number of AGN that we can see, we could have up to twice as many AGN in this image that we just don't see because they're hiding. And this is where the result from this talk is effectively that we found a heavily obscured AGN abundance of 35%, plus or minus 9%. And this is the first measurement of this heavily obscured abundance that's actually compatible with those predictions that I was talking about on the previous slide. Just to put it into perspective of the sort of difference that we find with previous surveys, here I've conservatively shown the distribution of obscuration, ranging from heavily obscured to unobscured AGN in local surveys. So of surveys of actively growing supermassive black holes in our nearby cosmological volume. And typically the fraction that's actually identified is less than 15%. Right. And so what this actually means is that one of the most elusive populations of AGN is actually one of the most common, because it's predicted to be up to 50% of the AGN as they grow. So given this difference, but way back in 2017, we sort of posed a question, right? We thought, instead of trying to find every growing supermassive black hole in our nearby cosmological volume, why don't we not try and do that, and instead try and just find unobscured and obscured AGN approximately equally well. That way, we won't have the firm conclusion of the absolute number, but we will know the rough proportions of heavily obscured AGN to try and work out what we should be aiming for when we try and detect these things. And the main way that we did that was that we relied on the infrared. Right? So as you can see in this geometry that we'll move in a sec, and also this lovely picture of me in the infrared, material and obscuring material in the case of AGN, or my body in the case of warm-blooded mammals, they re-radiate that hot energy into, or that warmth into, the infrared. And so it means that it's very beneficial for when you're studying AGN obscuration, because it means that when you obscure geometry, it's approximately the same brightness on the sky as the obscure geometry. And so it means that it's actually in benefit to have obscured AGN and unobscured AGN. We then combined that with a very large new star legacy program, combining new and archival data amounting to around 1,000 hours of NuSTAR time. And the whole point of having NuSTAR is that in X-rays, it's all well and good to be able to study the unobscured geometries like I'm showing here. This is an approximate cartoon of what you would see if you had high energy X-ray eyes. But it's not until you really see the most obscured geometries, which I'm showing here, that you're only able to see a tiny residual amount of X-ray light due to scattering. Right. So that tiny amount of escaping light is extremely faint. It's around 1,000th of the amount of flux of the actual intrinsic source. And so what you need is extremely high sensitivity at the highest energies that you can in X-rays. And that's what NuSTAR provides. NuSTAR is the most sensitive high energy X-ray telescope in orbit. And it's extremely useful for trying to understand heavily obscured AGN and not misunderstanding heavily obscured AGN when you only have limited data. So our main result is that this is the breakup of our distribution of different levels of obscuration. We find that the heavily obscured fraction in our sample is 35 plus or minus 9%. But also we find that there's roughly equal proportions of obscured, and heavily obscured AGN in the sample, which some maybe expect if you have a selection method that detects unobscured and obscured AGN roughly equal well. And so this is really exciting because we think that this is an ideal sample to follow up in the future to try and understand AGN growth or black hole growth in an obscuration unbiased manner. So just to finish with the implications, firstly, without proper knowledge of the abundance of supermassive black holes or growing supermassive black holes in general, our understanding of galaxy evolution is effectively incomplete. NuLANDS finds obscured and unobscured AGN approximately equally well, and the main result from that is that we find 35 plus or minus 9% are heavily obscured. But as I said earlier, the whole point of NuLANDS is not to find every AGN first within a certain volume. So it does beg the question, if at least 35 plus or minus 9% of our nearest cosmic neighbors are heavily obscured, where are they? And that will be some future work for me to hopefully carry out. So with that, thank you for your time, and yeah.
All clear? Awesome. All right, good morning, everyone. I am Midshipman Olivia Achenbach, an astrophysics major at the United States Naval Academy. Today, I'm going to present to you work I did over a summer internship in 2024 with my research advisor, Dr. Nyland, at the Naval Research Laboratory. So first off, I want to start off with something a little bit close to home and the motivation behind this project. For all future naval officers of the United States Naval Academy, we are taught celestial navigation. And for the midshipmen in the crowd, we're very familiar with STELLA, the system to estimate latitude and longitude astronomically. Within this little image here, you can see that we use planets and luminous stars and measure them in order to correct our positioning. And we also use visual observations with a sextant. This tool we use to measure stars and their positions in reference to the horizon to correct our positioning for navigation. However, more fundamental to these systems that we use in the fleet and for systems you are all familiar with like global positioning systems, is the International Celestial Reference Frame. It consists of thousands of quasars, which, as presented before, are supermassive black holes actively accreting matter at the center of galaxies. And also, they are all these dots that you see in this little image here. We use these to provide detailed corrections to alignment for positioning systems. And this little image here is an artist's depiction of a galaxy with an active quasar emitting radio jets. However, we don't really understand the physics of these quasars or their jets, and it is really important to understand this physics to maintain navigation systems and the ICRF. Specifically, only 1 to 10% of quasars emit jets. We don't know why. Jets are powerful streaming radio, emitting plasma, traveling at nearly the speed of light. And then you see in this image here, these little pink emission features are radio jets. They can extend far beyond the extent of their host galaxy. Another question we don't really quite understand the answer to is how are quasar jets triggered? There's two main arguments. First, here, where it's a merging process between galaxies, where two large galaxies merge to one, and this influx of matter fuels a quasar to emit jets, or secular processes, those inherent to a galaxy itself, as shown in this image here. If we want to understand the unknown questions about quasar jets that I presented to you, we need to identify and study quasar jets when they're young in order to understand their triggering. Recently, NuLANDS et al. 2020 led a study discovering a sample of newborn quasar jets. The discovery was made by comparing new and old radio surveys captured by the Very Large Array. The two surveys, pictured to the right here, first in VLAS, where in the 1990s, first radio emission features in our sample of quasars, and then in 2017, the Very Large Array Sky Survey, or VLAS, discovered that J0742-2704, one of the quasars in our sample, and the other quasars in our sample, started emitting newborn jets. This was captured 10 to 20 years relatively to us. And this here is the artist's depiction of a radio quiet, a radio quiet versus newborn radio jet. Sorry, this is touchy. To understand the triggering of jets in the sample, we needed a high resolution observation to measure the morphology of our host galaxy that emitted newborn jets, to also understand the properties of its environment that triggered these radio jets. J0742-2704 was observed using the Wide Field Camera 3 on the Hubble Space Telescope in near infrared. This beautiful image to the right, gorgeous, I think about this all the time, is the image of our quasar. You can see in the center here is J0742-2704. You can also see that there's faint hints of a tidal tail already in the high resolution of this image. Canyon here and a beautiful ring galaxy to the right. So, to determine the morphology of this host using the high resolution of the Hubble Space Telescope, we needed to remove the contribution of the quasar's light, which dominates the image and obscures most of the host galaxy's morphology. First, we had to model the point spread function here. A point spread function is the response of the instrument, to a bright point source in the image, which was our quasar. It almost acts like a selfie of the instrument. Then the point spread function needs to be multiplied right here by the surface brightness profile of the host galaxy. So we modeled that as a simple disk. Finally, the difference between these two, as conceptually shown in this image here, leaves the residual image to the far right. And at first, looking at this residual image, we saw a spiral structure. At first, I thought I completely messed up during our research because we both predicted, because with such a large supermassive black hole at the center, we'd see an elliptical galaxy. So based on our initial lenstronomy modeling, we expanded our modeling to include some additional sources in the vicinity of the quasar to look more into this peculiar system. These series of figures show the quasar, its tidal companion, that little small dot right there, the beautiful ring galaxy, and two stars within this system. This improved the modeling result greatly, as the residual image to the far right exemplifies that prominent tidal tail you see, the spiral structure within J0742-2704, and this is a clear sign of an interaction that could have triggered the newborn jets. This was extremely exciting news, and we looked into this further to see if there's a story to tell. So, to look into the history of this interaction, we wanted to see radial lobes of a previous interaction. We were excited to see that our quasar J0742-2704 in fact had old quasar lobes, remnants of radio jets detected by LOFAR, a low-frequency radio telescope. This is extremely rare and exciting news. In the picture to the right, the contours depict the old remnant lobes picked up by LOFAR that you can see, extending hundreds, thousands of kiloparsecs. So to show a visual of this story we're trying to model, this depicts our working model that I termed a cosmic dance happening between our spiral galaxy and our companion galaxy. We start with a galactic interaction in one, then after a long delay in time, a radio jet forms in this little artist depiction here. Then the lobes expand and eventually fade to produce old remnant lobes like these large emission features shown here in pink. Then a long time delay occurs and the cycle continues to potentially trigger new jets, like in J0742, 2704. And as a summary, I just wanted to cover that we used ground-based radio sky surveys and the Hubble Space Telescope for its superior optical resolution to image and reveal the physics of jet triggering. Furthermore, we believe that powerful quasar jets may be re-triggered by galaxy interactions in a term we coined the cosmic dance happening in our system. To the right, you can see like we highlighted the tidal tail, our quasar, and our ring galaxy. Thank you so much for your time. If you would like more information, please contact myself, Dr. NuLANDS, the Naval Research Laboratory PAO team, and also check out my iPoster. I did present right before this, but I'll be happy to talk about that and more. And this research will also be published in the Astrophysical Journal very soon. Thank you so much.
I do. Wonderful. Thank you so much to all of our speakers. We are now going to go ahead and move into Q&A. Just a reminder for anybody asking questions to please identify yourself and your affiliation and who your question is for. And reminder for our speakers up here to talk directly into the mics in front of you when you do answer. Let's go ahead and start with Ethan.
Hi there, I'm Ethan Siegel from Starts With a Bang on Big Think. And this question, it's probably for Megan, but if Eileen takes it, I will understand. I want to know, you talked about this scenario for what could have caused this, that you said we have tidal disruption, and we think this originates from an object that became a white dwarf and from mid-2022 until the present has in-spiraled from a period of about 18 minutes to a period about 7 minutes. You have X-ray data that goes back to mid-2018. So I'm curious what's happening between 2018 and 2022 before this part started, and is that consistent with this same scenario you put forth about a white dwarf in spiraling?
Yeah, that's a great question. I could have given you a whole other talk on what happened from 2018 onward. So this source, the reason why we've tracked it so extensively in the X-rays is because it did something in 2018 that we've never seen before, which is that what was producing the majority of the X-ray emission, in particular the hard X-ray emission, the high energy X-rays, was destroyed. Now this is called the X-ray corona. And we have basically watched the corona reform in real time, and that corona is potentially related to the base of the jet. So I can tell you on the variability side of things, you saw one of the light curves. It didn't seem to show any sort of periodicity. However, our light curves are relatively short, and so it's kind of difficult to probe much longer timescales than like an hour. So I do think it is consistent. We have a bit of a gap of about 1.5 years in our XMM observations from 2021 to mid-2022. So we can't say much about it. But yeah, we're working on piecing together the full picture of the outburst, but I do think it's consistent. And yeah, we're going to go look back at some of the nicer data as well in future follow-up work. It's just a little bit more complicated because NICER gives these really short snapshots that make it difficult to see. They give you snapshots on the order of, 10 minutes to an hour, which make it difficult to see periods of 10 minutes or so.
Hi, Ross Silver from NASA Goddard, and this is also for Megan. So you talked how when the period went from 18 minutes down to 7 from 2022 to now. And then you said that you would like, if possible, for it to be also observed in the future by Lisa. Is there any guess if you think this system will still exist in this sense at the time that it's launched and ready in 2030-ish, something, 5, 9, who knows?
Yeah, I mean, it's a good question. One of the things that I've learned with this source is that we never really know what's going to happen next. So who knows? Oscillations might turn off in a few years, but if it is from this white dwarf, we have some rough estimate of how much mass it's losing, and I think it should be able to stick around for quite a while. But it's really, yeah, I have no idea. We'll see.
Hao Zhang from NASA Goddard. So I actually have two questions. The first one is still for Megan and also maybe Eileen. So like the two scenarios you talked about, in the case like it's a wide dwarf there. So my question is like if that's the case, then how that's related to the jet launching, and especially like since your period is getting shorter and shorter, how do you expect that the jet radiation signatures might be affected by that? So, but if in the case that is actually jet oscillation, then do you have like other ways to confirm that it's jet oscillation at all?
Yeah, so I think it's difficult to connect the white dwarf case directly to the jet launching scenario. I don't think that we can't do it. We just don't know exactly how to do it right now. In terms of the one reason why we really like this white dwarf scenario is because it makes this clear prediction for LISA, for the next generation gravitational wave detectors. It's a little bit more tricky with these jet oscillations. We're not exactly sure how to check them, but I will say that we're continuing to follow this source, and there are some different things that could tell us about. So right now, the period is kind of tracing how the X-ray brightness is changing, which is one thing that tells us maybe it's connected to that base of the jet. But if that changes over time, then we can probably lean more into this white dwarf scenario. Yeah, I think maybe Eileen can talk more about this, but the actual like the radio jets that are expanding are coming from much further away from the black hole than where these X-rays are coming from. These X-rays have to be coming from very, very close to the event horizon, whereas Eileen is talking about things on much larger scales.
Yeah, just to confirm that's the case. So the X-ray emission is so compact, it's coming from such a small region that although there could be radio waves emitted, we won't ever see them. So they're basically lost to us. And what we see is happening on much larger scales. And that disconnect always makes it a little bit tricky to make an exact connection between what we see in the radio and what we see in the X-rays in all cases. So.
Okay, and thanks. And I have a second question actually for Olivia. So I'm always curious about like say if we like one day we figure out how exactly say like quasars can launch a jet and how the physical conditions they look like, how exactly that can say help to contribute to say like the navigation systems, things like that. Do you have a rough idea?
Yes, it's a really great question. So we can use these quasars and their jet physics to help align our positioning systems, but we don't really know how to predict which ones are going to exhibit jets. And sometimes ones that are exhibiting jets or ones that have newborn jets, these jets have the chance to offset the positions of these quasars in that international celestial reference frame I talked about. So say it's like a milli-arc second shift due to a jet can be scaled to a full. Critical to understand how these jets work, and we can learn how to predict them so we can accommodate that in our navigational systems. Thank you.
Do we have any questions online?
This question is from Monica Young at Sky and Telescope for Eileen. What's the expected evolution of a compact jet generated by a tidal disruption event? That is, how long could it get and how long could it last?
This is such a great question, and I wish I knew the answer. So yeah, this is interesting because we've seen in very rare cases actual tidal disruption events. So again, those are different from AGN. They're black holes that are usually a bit smaller and they weren't active before. And there are cases where that tidal disruption event definitely triggered a jet. The timescale is not the 1,000-year timescale that we have for the compact symmetric objects. So that would be a difference. And I think right now there's still a lot of theoretical work that needs to be done to better understand, what is going to drive the difference between an tidal disruption in a already active system versus not active. But at least if we believe that hypothesis that CSOs are triggered by one-time ingestion, apparently the lifetime extends up to 1,000 years, and that's kind of the hard cutoff. So we're certainly going to continue following this source, maybe for 1,000 years, I don't know. And if the fun thing about it is we really don't know what it's going to do. It may continue to be exactly this bright for the rest of my life, and it may turn off tomorrow. Certainly we'll learn something when that happens.
Hi, this is Ethan again, from Starts with a Bang on Big Think, and I have some follow-up questions about this event because I think it's really cool. One of the things I want to know is if the features that were generated in the early stages by the TDE, do they suggest that there was something initially bigger than a white dwarf that got disrupted? And is the white dwarf the remnant of that? Or do you suspect, oh, this was always a white dwarf and it just kind of got TDE'd somehow and then it, blah, blah, blah for a while, we don't know, and it migrated?
Yeah, good question. And one that we've actually spent quite a bit of time thinking about. So potentially you could disrupt kind of a star and leave behind a remnant core that could have been this white dwarf. But it turns out that dynamically speaking, it's actually very difficult to go from something that is tidally disrupted down to something that's very close to the black hole in this kind of like circular orbit on timescales of like 4 to 5 years. So it's possible, but you need pretty extreme conditions. This source is crazy, so maybe extreme conditions aren't unreasonable. Or this could be something that, existed in the disk previously and has now been kind of making its way slowly towards that black hole. So it's kind of unclear, but if it is directly related to the tidal disruption event in 2018, it needs to be a pretty extreme scenario.
Yes, I have a few questions myself. This is Rick Feinberg from the AAS Sky and Telescope, Astronomy for Dummies, and everywhere else. So I got questions for everybody. Let me see. I think a couple were answered already, thanks to Ethan's questions. Can you clarify, this is for Eileen first, this huge brightening, was it first discovered in X-rays or was there an optical counterpart to it, and which came first?
In the 2018 case, it was, I believe, it was an optical trigger. So it was seen with one of these surveys that's looking for supernovae, actually. But the later one, what we saw was basically a continued increase in the X-rays first, and that was actually particularly in the soft X-rays. So which is interesting. And then the radio was delayed. So there was a sort of a few months timescale where we didn't see any uptick in the radio, and then all of a sudden it went up very fast, so fast it was almost suspicious. So we think that it's very possible the jet actually did exist before that, and it was being screened, and so there was some hot gas that can basically interfere with your ability to see it, and then it kind of broke through, and that would explain why it just went exponentially brighter all of a sudden to this plateau that it was at.
Okay, my next question is for either you or Megan. You both showed the graph of the X-ray light curve. And before the big outburst, there was a huge drop. Now, was that what you were saying in response to Ethan? That was the X-ray corona turning off?
Yes, yeah. So our first observations in the X-rays after the 2018 optical outburst showed a very soft X-ray spectrum, more reminiscent of what we see in tidal disruption events and not really like in active galaxies. And then the X-rays just plummeted. And actually they were basically undetected for, I don't know, a few weeks, an order of a month, and then they turned back on. So this was it was a bit delayed with respect to the optical, but also we didn't start observing in the X-rays until about 2 months after the optical peak started. So.
Okay. I think also, Megan, you mentioned that the 10-minute period implied that the source of the oscillations was very close to the edge of the accretion disk. Inner edge or outer edge?
Inner edge. I mean, it's like very, very close to the black hole's event horizon.
Okay. this is also, I suppose, related to Ethan's question about the nature of this companion being a white dwarf. I was just going to ask, if are you basing that on its mass, or I mean, why couldn't it be a similarly massed supergiant, which would seem to throw a lot more material onto a black hole?
Yeah, it's a great question. So white dwarfs are very compact. And the important point here is that the tides from the supermassive black hole would rip a normal star to shreds, much further away from the black hole. So we really can't push a star that close to the black hole's event horizon.
Question for Peter. Is that right? Can I
Yes.
keep going? Yeah.
Go ahead.
Okay. Okay, so you were comparing the X-rays to the infrared. And you told us that the X-ray data was coming from NuStar, but I don't recall you saying where you got your IR data.
Yes, thank you. Yeah, so the infrared actually comes from IRAS,
Okay.
which launched in 1983. So
Okay.
yeah, 4-decade-old data, basically.
And for Olivia, let's see, I want to make sure I got this right. Maybe I don't. Well, yeah, okay. For you, my question was, when you showed the LOFAR data, what was the scale of that compared to the wide field camera image from Hubble that you showed? I mean, was the Hubble image just the very center of that giant LOFAR view?
Are you talking about like how we changed like the orientation?
Well, how you knew that those lobes, the radio lobes, were so much older? I mean, right? So they were farther away, presumably. Just asking where was the activity that you saw in relation to that LOFAR field?
Right.
Just right in the very center, and like a dot, or was it?
So in the scale of that photo, you wouldn't be able to see those newborn jets. Like that is pertaining to your question. Those old remnant radial lobes are extending far beyond the extent of J07 to 2704 to the point where like you wouldn't be able to see our newborn jets. Those contour lines are way far away.
Okay.
Yeah.
And then I realized I had one more question for Megan. So on the slides, it said millihertz oscillations, but then you talked about periods of minutes.
Yeah.
So I'm just confused where the millihertz came from.
Yeah, so we said millihertz because that's so millihertz is the frequency. It roughly corresponds to 10-minute periods. I think it's nice to talk in periods because 10 minutes is roughly how long I stood up there and talked for. Millihertz means less, but
Okay.
Lisa is going to detect things in the millihertz regime, so it's
Okay.
nice. It's a nice connection to Lisa.
Okay.
Yeah.
Good. That's it for me.
Great. We do have a few more in the room, and it looks like maybe another online. Let's start in the room over here.
Thank you. This question is for Olivia Achenbach. Wonderful use of the Hubble Space Telescope. I'm excited about that. I was wondering if in your model, given this kind of episodic possibility of these jets, would you say that its companion is orbiting the galaxy? Like, are these galaxies in some kind of mutual orbit rather than a kind of one-time grazing pass? Or do you have any idea of the dynamics going on?
Yeah, that's a really great question. So we're looking more and more into the dynamics of this galaxy, and Dr. Nyland has proposed like further surveys like to examine this galaxy. I would love to get a James Webb Space Telescope image, but we do believe that they're interacting like in that term, the cosmic dance, like the energy of that spiral is feeding off of like the energy of that companion in some way, shape, or form. It could be in orbit. We would just have to look more into the history, which we are.
Let's take the one online first.
This question is from Camille Carlisle at Sky and Telescope for Peter. This is a follow-up on Rick's previous question. I'm surprised that you used IRAS data instead of higher resolution data from, say, WISE. Why IRAS? What could higher resolution infrared data do for your project?
Yeah, that's a great question. So in terms of actually using IRAS, the primary interest was that to reach further infrared wavelengths, because there was previous studies that suggested that selecting in the mid to far infrared regime could select unobscured and obscured AGN roughly equally well. And it also turned out that IRAS was quite well matched in sensitivity to the sensitivity for NuStar. In terms of near, In the near infrared, you tend to have better angular resolution, and you could resolve similar fractions. It can be a little bit trickier to not select to select unobscured and obscured equally well, though, as you get closer and closer to the optical.
We've got, let's start in the back of the room, one more back there.
You got to move up closer next time.
Yeah, it's a follow-up question for Olivia. So, okay, this is Hao Zhenjiang from NASA Goddard again. So, since you mentioned about if the quasar launches a jet, then it may impact the accuracy of locating the quasar in the ICRF, right? But we know, from physics, that usually those radio jets or lobes, they are polarized because they are emitting in synchrotron, and the quasars themselves. At the core, they are not so highly polarized. Then if you also include the polarization information from radio telescope, which most radio telescopes actually have that by design. In that case, can you already just improve the accuracy of the ICRF?
That's a really great question. I'm not too familiar with obtaining this jet physics and aligning navigation, but I would love to learn more. Thank you for your question. You can also look more into information about what's going on in this system and the more of the quasars in our sample in Nyland et al. 2020. But as of right now, I do not have the answer for your question. All right.
Had another one up. Oh, okay, go ahead.
Question for Peter. Ryan Fifley, NASA Goddard. So your percentages for great work with NuLANDS. So you have a 35% Compton thick or heavily obscured, and then another 37% for obscured. So that's like 70% obscured. Do you foresee this being a problem as we try to push to higher redshifts with future X-ray probes, trying to understand the Compton thick or heavily obscured?
That's a fantastic question. Yeah, so there's a few aspects to that. One is the benefit of going to high redshift in some sense, because if you only have soft X-ray telescopes at higher redshift, you have the redshift effect, and so higher energies are actually what you detect in soft X-rays, and so you can start to detect like new star at higher redshifts. But yeah, it is a problem because in a way the best constraints you can get will always be in the local universe. Things are always brighter the closer they are. And so, yeah, it could be a useful consideration to take in mind when trying to understand the obscuration properties at higher redshift.
I forgot to identify myself last time. Jennifer Wiseman, NASA Goddard. Another question for Peter. Can you speculate, at least as you're understanding more about how many of these AGNs are actually obscured, how that affects our understanding of how AGNs affect the star formation history in these galaxies? I mean, there's always a lot of aggressive study as to whether AGNs actually stimulate star formation or in some sense quench it, or, there's different studies. So this may be a push way beyond what your study is looking at, but I just wondered if you had any speculation on the sort of cosmological significance of what you're finding in terms of the percentage of obscured AGNs and how prevalent AGNs are in the universe.
Yeah, thank you. That's a really interesting question. So I think on the basis of it, if there are the sort of results of trying to understand the interplay of star formation versus activity of the black hole, it does kind of hinge down to an understanding of just how many black holes are active in the first place. And so just from the base level, having a substantially higher fraction of AGN that we previously just didn't know about, that can really impact the interplay of both, because at higher redshift, where it might be harder to know if something's an AGN or not, or star formation, then it kind of pushes for having more multi-wavelength data, where you can really pin down the roles of star formation as opposed to black hole accretion. Thanks.
All right, we're going to go ahead and wrap this up because we are at time. Thank you so much again to all of our speakers, our presenters. Let's give them another round. And thank you to their PIOs and their institutions for helping with press releases and prepping them and everything. And thank you to all of you for being here. Really appreciate it. We hope you will come back and join us this afternoon for our press conference at 2:15, which is titled Supernovae and Massive Stars. And we hope that you will stop by the press meet and greet at 12:45 in the press office as well.